This video is about developing a rectangle to rectangle transition with the top rotated 90 degrees to the base. So I've drawn it in third angle projection. That's what we use here in New Zealand. So the plan view is up the top, front elevation is in underneath it, and the end elevation comes out to the, well, I've got the right hand side one. I could also do the left hand side view if I wanted. From that position, I've drawn the isometric sketch of it, or the isometric projection of it. The orange lines represent a proper rectangle, which would be 140 wide by 100 millimeters. And the total height of this transition is 115 millimeters. I show it right on the left hand side here, and the front elevation shows exactly the same dimension. So there's different ways of doing it. You could make it in 4 pieces and weld down the 4 corners. I've got my joint line at the bottom left hand corner in the plan view. When you look at the front elevation, it's this line going from the bottom left hand corner to the top left hand corner, and over in the isometric it's this line on the outside from 1 up to D, 1 to D, and down here I would have 1 and D at the top. So in order to develop it as a triangulated pattern, each face needs to be broken into triangles so that we can actually develop it. So what I'm going to do is I'm going to break each face here, the left hand face, top right hand face, and the bottom face, which you can only see a portion of, into triangles. So what I'm going to do is I'm going to draw a line, and the first one I'm going to draw a line from 1 up to 4. The top face, I will draw a line from 2 across to B. The right hand face, I'll draw a line from 3 down to C. And for the last face, the bottom face, which is the front face, I'm going to draw it from 1 across to C. So if I was to look in at the front face, that line would be going from 1 down at the bottom up to C. This is C up here, this is 1 down here. So this line in plan view is this line in front elevation. The face is broken into 2 triangles. We could take these lines and work out the elevational height, put them across the elevational height and determine what their true lengths are. But I've calculated every single line over here on the right hand side using Pythagoras' theorem. So for instance, this line here, C to 4, in plan view it's 40 mils in one direction. It's 30 millimeters across this face. Here's the 30 here, there's the 40 there, and at the same time it's 115 mils high. So that line over here in the isometric sketch is this line here. This line here is 115 millimeters high. This line, from this blue point here to this intersection point here is the 30 millimeters shown there, and from C at the top here, this corner at the top here, back to that point is 40. So it goes up 115 mils, across 30 millimeters, and forward 30 millimeters, and that's how we can determine the length of that line. So from 4 to C, if I come over here, 4 to C, the dimensions I've got 30 millimeters squared plus 40 millimeters squared plus 115 millimeters squared. So what you're going to do, if you're going to do this, is you're going to get a scientific calculator. You're simply going to use the square root symbol. You're going to type in, put the square root symbol in, put 30 millimeters squared plus 40 millimeters squared plus 115 millimeters squared, and when you push equals, you'll get a length for that line there of 125.399 millimeters. I've done it to 3 decimal places just because I find it easier to do those things instead of rounding it. You won't get everything perfect. So Pythagoras' theorem, we can only use c equals the square root of a squared plus b squared, but we can actually put in another figure. So effectively it's like having d equals the square root of a squared plus b squared plus c squared. And we will get lengths for all of these lengths that are required. So I've got this one, this here, this one, here, 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 and here. All these 8 lengths have been calculated over on the right hand side. The rectangle on the top is flat. The rectangle on the bottom is flat, so they're all true lengths. So once you've done all the calculations, you can then start to lay the pattern out. So I'm going to draw the pattern rather quickly, as quick as I can. So what we want to do, because the joint line is at this point down here, I'm going to start with the baseline of 140 millimeters. So we'll start off here with a line. Actually, I just need to put the ribbon on for a moment and change to outlines and ribbon close. Get rid of the ribbon again. So I'm drawing lines here, a line here, 140 millimeters across. And that is going to, because I'm going to lay it out, I'm going to get the 2 and the 3. And I'm going to copy those, clipboard, copy with a base point. That's my base point. So I'm going to bring that over here and I'm going to paste that on there. So there's my numbers for my line. So what I want from line number 3 on the right hand side, I want this length here from 3 up to B. So appeared 128.938. So from point C, drawing a circle, 128.938. Now using Autocad, it's not like using a set of dividers on a sheet of metal. I could draw arcs, but I find it a lot easier to do circles. So the next line I want here is from 2 to A. Over here, 2 to A tells me that it is 135 millimeters long. So from 2 to A, draw a circle, 135 millimeters. And I want to get this, to make 2 triangles, I need to use this length here to fix a point. I've got a circle drawn from 3 to B and from 2 to A, but I need to fix a point at the top. So I'm going to use this line here, 2 to B. So if I come down here, 2 to B, I've got 166.08, and that's 2 to B. So I come over here, from 2, 166.08, and that's lining up with this circle here. So what I'm going to do is I'm just going to draw a really small circle at the top, 10 mils, and I'm going to trim this out. If you watch my other videos, you'll see how I do this. So that's the point that I want. From that position, the top of this trapezium face is from A to B, which is 60 millimeters. Down here it says 60. So I'm going to put a point, draw a circle, 60 millimeters, and that gives me an intersection point here. So 10 mil circle, 10 mil circle. I need to type in 10 mils for this since I've gone and used 60 for the other one. So 10 mils, trim that out, get rid of that. So there's my lines. Where's my line? Goes from 3 up to B, across to A. I missed that. Pick that up and go to that point there. And from 2 up to A, get rid of that. So my line that I did for my triangle, that's that line there from 2 to B at the top. So I'm going to take those 2 figures there, copy those with a base point, that point there, bring it over to here, paste it on. So there's my points there. Going to develop this face here back to the joint line. So I've already got point 2 and A. I need A to D, I need 2 to 1, and I need 1 to D, and also 1 to A. So the very top one is 90 millimeters. That's a 90 millimeter line. So I'm going to draw a circle there at 90 millimeters. The line on the base is actually 100 mils. So I'm going to draw a 100 millimeter line. Sorry, circle. Not thinking. 100 millimeters. To fix that point, I need to get this line from A down to 1. So over here we have A1, and that's 135 millimeters long. A1, so come over here, draw a circle, 135. This is the point right out on the outside here. So 10 millimeters, trim it out. Click on that, get rid of that, get rid of that. Get rid of that piece there, and then what we want to do is to take this line, this joint line, from 1 up to D. So over here we have 1 to D at the top. It has a length of 131.624. Circle 131.624. Draw a little circle up the top there. 10 millimeters, trim that out, get rid of that. So lines, drawing that in, up to that point there, down to there, back to there. The line that I used to make the 2 triangles is this one here, back to that intersection point, so I can get rid of those 2 points. Those 2 points. The top piece, the one on the top, is D. Just going to copy that. Just number it, paste it. So that's point D. Point 1. Control C. Back over to here, Control V, put that there. So that's the outside edge there at that point. The next face I'm going to lay off is this face here. I've got this line here, 3 to B. I need from 3 to 4, 4 to C, B to C, and this long line from 3 to C. So B to C is 90 millimeters. 90 millimeters. The base is 100 millimeters, so from there 100. I'm going from 3 to C at the top, and 3 to C over here. What do we got? 183.643. So I put that in point number 3. Circle 183.643. So it sits quite high. Circle there, 10 millimeters. Trim that out. 1, 2, get rid of that. Then the length that I need is to go, so that's C up there, and I need to get back down to 4, so the length I'm looking for is C4. C4 is 125. Circle from that point, 125.399. Put that on there, 10 millimeters. Trim that out. So that's the next face. So I'm going to take a line from down here at 3 up to 4 up to C at the top and back to B. Get rid of those points. Get rid of this over here. Actually, I'm going to copy this and move it over a bit so I'm not taking up as much of the screen. Get it over here now that I've worked out where I am. So I want point number 4, Control C over to here, Control V, point 4 is there, and at the top I want C, Control C, Control V, and we did our diagonal from 3 up to C, so 3 up to C. So the last face is the very front face. We can only see a portion of it. We can see it in front elevation, but we can only see a very small portion of it through this hole here. So what I need is from 4 across to 1. I need C across to D. So 4 to 1 is a circle of 140 millimeters. 140. C to D is 60 millimeters. And the line this time that I wanted, come on Mark, is 1 to C. So 1 to C down here is 164.088. So into C, a circle of 164.088. Do a little circle there, 10 millimeters. Trim that out. Get rid of that, get rid of that, get rid of that. The length from, so D to 1 was up the top 131. I've got that written down, 131.624. So a circle at this point here, 31.624. Draw my lines in from 4 across to 1 up to D and back to C. Can take those out, take that out, take that out. And the points that I want are 1, Control C, over to here, Control V, and the top point is the D, Control C, and Control, yeah, there we go. And the line that I did was from 1 up to C on that one. So I did from 1 to C, line 1 up to C. So I'm just going to turn the ribbon on again, and I'm going to highlight those points, which are my triangles, or my projection lines for my triangles. And that's it done. So when you do a calculated transition like this, I've drawn out the isometric view, I've drawn the front elevation, I've projected across and got my end elevation. I actually don't need any of that. All I need is a plan view, and I just need to work out what the offsets are for each and every line. So for instance, 3 to B, it was 30 millimeters across, it's 50 millimeters this way, and it's 115 millimeters high. So it looks quite complicated when you start to see it on the page like it is, but it's actually very simple. If you just do a drawing like that and work out what the offsets are, the 3 offsets, you can put it through the calculator using Pythagoras' theorem, putting the 3 numbers in, and it will give you the true length that you're looking for. And if you can do that, all you're going to do is write them down and then place them on the sheet. I projected it, done the pattern development for the inside of the transition. We're looking at the inside face. The only way you could fold this up is actually on a press brake. If you did it in a finger folder or a straight folder, box and pan folder, you wouldn't be able to get your last fold because it would start to crush the third face. So doing it on a press brake, you'd fold one fold, you'd fold the other, and then you would finish with this center fold, and it would wrap around the tooling. Sometimes you've got to hang it out the end of the press brake to do it. Doesn't really matter so long as you can do it. But that's how you would calculate a transition if you were doing it as one piece with one joint, instead of doing it in 4 pieces, is basically what I want to say. It only works for a transition that has the rectangle on the top flat and the base line flat. They must be parallel to each other. If it is inclined, if one face is shorter than the other and it's coming up on an angle, the top face and the bottom face will be flat, but the two sides will have to have a fold in them. Otherwise you'll have scalloped faces. I'll do a drawing on how to do that. So a calculated rectangle to rectangle transition developed with triangulation, simply calculated instead of drawing it all out and trying to work out what the true lengths of these 8 lines were over the elevational height. If you can use a calculator, you should be able to run it through this formula here and determine those lengths.